Hello everyone and welcome to the webinar. Before I start, I wanted to mention that the webinar will be recorded and it will be available in our YouTube channel within a week. During the webinar, if you have any question, please feel free to type it in the chat section. And during the webinar and also at the end of the webinar, my friend and my colleague, Dr. Ladirza Azami, will help me to coordinate the question. If any question left and we couldn't get back to you throughout the webinar, we will answer your question with the email that you registered. Also, at the end of the webinar, I would appreciate if I can get your feedback because we are going to have two poll questions. So if you can stay to the end of the webinar and answer those questions, I really appreciate. I just wanted to double check with you guys. Can you guys see my screen and hear me?
Yes.
Excellent. Okay. I'm honored today to introduce to you the 3D discrete fracture network in RS3, which is one of the major features that we recently released in the program. I am Sina Moallemi. I am the project manager of RS3. Just for some of you that are not familiar with Rockscience, Rockscience is a world leader in developing innovative 2D and 3D softwares in civil mining and geotechnical engineering. From a team of only 4 people 25 years ago, now as you can see in the picture, the company has grown and now we are a team of 80 people. We have 4 offices and representatives all across the globe, and right now the number of our users has surpassed 10,000 in the world. Here you can see a full list of our products. We offer 19 top quality products tailored to meet all your civil and mining and geotechnical needs. One of the benefits of using Rockscience products is that they can communicate and talk to each other. For example, if you have a model in RS3, you can create a section, export it to RS2, so you don't need to recreate your geometry. You don't need to redefine your material property. In this image, you can see the Rockscience software ecosystem and how they are connected to each other. But today's focus is on RS3. About the agenda, first I'm gonna briefly introduce RS3 to you, the workflow in RS3, then the main topic of today, which is discrete fracture network, will be discussed, the overview of a DFN tool that we develop in the program. I continue with 2 demonstrations, so by the end of the demos, you should be able to define discrete fracture network, assign it to the geometry, and also edit the DFN. Then I show you 2 of the application of the DFN in 2 examples, and at the end, I wanted to introduce the 2 other features that we released recently in RS3. RS3 is our 3D general finite element package with a wide range of application. I can categorize that into mining engineering and civil engineering. For mining, you can do a slope stability, you can model large-scale mines, you can model sequential underground excavation, and now with the DFN, you can define the jointed rock masses. And for civil application, you can do consolidation, seepage analysis, dynamic analysis. With the tunnel designer tool that we offer in the program, you can define sequential excavation for tunnels, define different support elements such as liners, bolts, beams, and piles, and you can do deep and shallow excavation. Here you can see the workflow for model creation in RS3. First step is geometry creation. You can create your geometry within the program with the tools that we have, or if you already have the geometry, you can import it to the program. We have a powerful repair tool. So if it can check your geometry, it can find all the defects in the model that you imported and repair it for you. Next step is the material assignment. So in RS3, we have a comprehensive material library for both soil and rock. We have different constitutive models such as Moore-Coulomb, generalized Hooke-Brown, generalized anisotropy. Also, we have a borehole manager, so you can define the borehole, and then based on the location of them and the thickness of each layer, RS3 is capable to create the geometry for you. And then you need to do the divide all to find all the intersections between the volumes that you created. The first three parts are shared between all of our 3D packages at Rockscience. We actually had a separate webinar focusing on just model creation that me and my colleague and my friend Dr. Sina Moallemi did about a month ago. So if you are interested into that topic, I really recommend you to go and check the video out. Next step is loading and applying the boundary condition. Depending on the type of analysis you are doing, you can have a solid boundary condition, seepage boundary condition, or dynamic boundary condition. Then you can create the mesh. In RS3, we have 4-noded or 10-noded tetrahedral elements, so you can define the mesh, and then you can do the computation. In RS3, you can do SSR analysis, you can do coupled or uncoupled seepage, solid or fluid analysis, you can do dynamic simulation, and also in RS3, you are able to measure the natural frequency of your geometry. And at the end, you can see the results. I'm not going through the details of each of them because we don't have enough time, and the main topic of today is discrete fracture network. So when you go to the site or when you go to the nature and look at the rocks, you can see it contains of faults and joints that are created in geological process over millions of years. And you can also see the orientation of the joints and also the spacing of the joints. They can be either uniform or it can have a stochastic distribution. But the main thing here is the properties of intact rock and these joints can be completely different. So you have to measure these properties correctly and then assign them to the geometry. RS2 was the only 2D finite element geotechnical program that let the users to define this joint network and assign it to the model. And now we expanded this feature into the 3D. We added it to RS3, so now you can define the stochastic distribution for joint networks, add it to the model, and do the full analysis. In this version, in the first version of DFN, you can define parallel joints, cross joints, or you can either import DFN. And of course, for each of them, there are few parameters. You can have the spacing, orientation, the shape of the joints in case they are not infinite planes. You can modify all of them in the tool. I'm going to explain to them in detail during the demonstration. So when you open the Define DFN tool in RS3, you will see something similar to this window. It contains of 3 panels. In the left panel, you define the DFN set. Each DFN set can contain of one or multiple individual DFNs, and each of them could be either parallel joints, they could be cross joint, or any combination of them. And at the end, you are going to apply the DFN set to your geometry, not like one of these individuals that you define under the DFN set. And then when you click on each of the DFN, each individual DFNs that you define, you will see a list of parameters that you can play with, such as the spacing, the joint property, the length of the joint. And in the right panel, you can see the visualization of the distribution that you defined at the middle panel. Before I show you a demonstration, I just wanted to mention that we did a lot of verification for the DFN. We compared our results with other products such as like RS2, of course, and UDEC. Here, I just show you 3 examples. So we measured the stability of the jointed rock mass. We did the SSR analysis. So in this example, we only had one set of joints. In the other example, we had a combination of explicit joints and also the DFN and In the other example, we had a combination of two parallel DFN that are intersecting each other. And in all the cases, we calculated the critical SRF, and as you can see, the results are very close between all the programs. If you want to see the full list of this verification and see more detail about the examples that I just showed you, you can go to our website and go to the joint verification for RS3. Okay, so now let's dive into RS3 and see how we can define the DFN. So this is the slope that I already defined. I already did the divide all for it. You can see each of these layers are now a piece of the external. To define DFN, you need to go to Material menu. Under the joints, we have a new option called Discrete Fracture Network. You click Define DFN. Okay, when you open the DFN window, it starts by giving you a bounding box, and that's where you will see the distribution of the joints that you are defining. The size of this box is based on the dimension of the external boundary that you have defined already. Okay, so the first one, I'm going to start with a simple example. So I'm just renaming it to simple DFN. And then you click on these three dots, add parallel DFN. Okay, the moment I pick the parallel DFN, you can see the distribution of the joints are already shown based on the default parameters that defined in the program. The first thing you can change is the property of the joints. So I already defined a few properties for the joints. If you haven't defined, you can click on this pencil icon, and it takes you back to the joint properties, and now you can define the properties if you need. I picked the bedding property that I already defined. Then you can set the joints are infinite or no. I'm going to leave it as infinite joints. And for this example, I want to have a uniform distribution of 1.5 spacing between all the joints. The moment I change the property, you can see the visualization become invalid. And to see it one more time, you need to click on the preview button. So if I click on it, now you can see the distribution of the joints are updated. You can also change the orientation of the joints. So for this case, I'm going to change it to 60, and for this direction, 220. And if you preview, you can see the new orientation of the joints. Initial seed is basically the origin inside the box that the reference joint will be passed through that specific point. And from that location, the rest of the joints will be created based on the spacing and the orientation that you already input in the program. This location by default is random, but if you want to make sure the joint is passing from a specific location, you can input that parameter. So for example, I want the joint to pass from this specific location. And then you click preview, it will be updated. Okay, so this was the simplest DFN that we could create. Now let's go and do more advanced stuff. I'm going to click on the plus icon to add a new DFN set. I'm going to rename it to advanced DFN. I'm going to add a new parallel joint, but this time, instead of having uniform spacing, I want to have a stochastic distribution for the spacing. So I check this option, and now you can see there are different distribution functions that you can use in the program: uniform, normal, exponential, or log normal. I picked the normal distribution, and for this distribution, you need to define the mean value, a standard deviation, relative mean, and relative max. So I'm gonna have the mean value equal to 5 meter, a standard deviation of 3, relative mean and relative max equal to 2 and 6. If you click preview, you can see the spacing is not uniform anymore. One thing I wanted to mention about the relative mean and max. So all the spacing that you are seeing here, the minimum value of spacing is mean value minus relative mean, which is 3 meters, and the maximum spacing in this DFN that we created is mean value plus 6 meters, or which means 11 meters is the maximum spacing that we can have in this distribution. As you know, we can have multiple distribution that can be defined with these parameters. If you want to see to update the distribution of the joints based on the parameters you input, you can always go and ask the program to give you a new one by going selecting on this icon and picking the randomized selected DFN. And now you can see it updates the location and also the new, basically DFN, the new joint network created for me. And I also wanted to update the location of the orientation of the DFN, 30 and 7. Okay. Now under this DFN set, I want to add another parallel joint, but this time I want to have the joints to be non-infinite. So I create a new parallel joints, and I update the property to setting for non-infinite. So as you can see, now I am seeing both of the joints, both of the DFNs here, which might be a little bit harder for us to see the changes that we are applying to the second DFN. If you want to hide the first one, you can go to the visibility tab and then hide the first one. So now I'm only seeing the second one. Okay, so this time we want to have non-infinite joints. And if I click preview, now you can see the joints are not connected anymore. And also you see a list of new parameters that we can define, such as the length of the joints, length 1, length 2, or you can define, for example, the persistence between the joints. Okay, let me have some stochastic distribution for the length for both length 1 and length 2. I'm going to update it to 15, 6.8, 10, and 10. And for the second one, I'm not going to change the mean value. I just update the relative mean and max. And if you preview, now you see the length is not the same number. Basically, the length of them is not uniform. It's random now. The same thing for spacing that I covered earlier. So I just quickly update the parameters for you. And persistence. Persistence is basically defining the gap between the joints. If the persistence is equal to 1, and then you click preview, you can see the joints in the direction, in this direction, are now completely connected together. The lower the persistence is, the more gap you will see between the these planes. And also I can update the direction of them. Let's say 30 and 270. I click OK, and now the view is updated. And so by default, when you change it to be non-infinite joints, it's going to have a shape of quadrilateral. You can update it to be circular if you want to, or you can have, for example, ellipsoid if you want to have such distribution. I turn it back to circular. And don't forget to include the first DFN that we defined. So this joint set, this DFN set, contains of 2 parallel joints. Let's define another one, and I rename it to cross joint. And I go and define a cross joint DFN. So cross joint contains of 3 sets of joints. One is bedding. Let me update the properties. The moment I update the property, you can see the color also changes in the right panel. And The same thing for cross joint 1 and cross joint 2. So the cross joint contains of three sets of joints. That cross joint 1 and 2 are perpendicular to the bedding. For the orientation, beside the deep and deep direction, we have another parameter called angle. Angle is basically the angle between the cross joint 1 and 2 with respect to the normal direction of the bedding plane. So if I change it to, for example, 30, and you click preview, now you can see both cross joint 1 and cross joint 2 are rotated 30 degrees around the normal direction of the bedding plane. And also you can set the non-uniform distribution for bedding and cross joint 1 and cross joint 2. So I quickly update them for you. Maybe I just reduce it to 10 and 20, and the same thing here. Maybe 8 and 7. You click preview. Okay. In case your DFN is very complicated and you want to see more detail inside the DFN, we added a tool that you can define a cross section, and you can move the cross section and see what's exactly happening inside the DFN that you created. So that's a cool thing. If you are interested, you can use it later on. Okay. So now I defined 3 DFNs. Now let's go and see how can we assign it to the model. I click OK. There are 3 different ways to add the DFN. The first way is you go to the material, discrete fracture network, add DFN. Now a list of the materials will be show up here for you. For example, I want to assign the cross joint that we just defined to the bedrock. So I pick the bedrock, which is the bottom layer. I click OK. Then a new window opens up. It asks me which of the DFN that you defined you want to assign. I pick the cross joint, and then you can set the staging if you want the DFN comes in a specific stage or remove in a later stage. You can assign it here. For this example, we only have one stage, so it's not relevant. You can click on the preview to see the distribution of that. And if you want to move the DFN a little bit, like change the location, you can update the placement by changing it, changing the values. You can move the DFN. If you click OK, the DFN will be assigned to the bottom layer. And you can see 3 sets of joints that we had for the cross joint is also added to the visibility tree. You can like update the parameters, the property of the joint here. But if you want to delete only one of them, all the DFNs in that set will be removed, because these cross joints, they're all connected together. You cannot have only one of them or 2 of them. All 3 of them will be together or will be deleted together. The second way to add DFN is to pick the multiple volume, and this volume has to be external volumes, by the way. You pick them in advance, then go to the material, discrete fracture network, add DFN, and then you can say, okay, add advanced DFN for me. And then you can click OK. And now that DFN has been added to the model. If you want to edit the DFNs before you do the divide all, you can select them, click on edit, and then click on the this pencil button, and it takes you back to the define DFN or edit DFN window. Then you can pick the DFN you are interested to update. For example, let's change the deep here. Let's increase it to 60. And then if you click OK, it will be updated here for you. So that's how you can edit the DFN. The third way to assign the DFN is to create a control volume. Sometimes you don't want to have to assign the DFN to the whole layer or everywhere that has the specific material. You want to assign it on a specific region. To do that, you need to define a control volume. So I click on control volume, then the program asks you to define the origin that you want, define the location that you want to have DFN in that. So let me update the coordinate of the box. -10, 12, 25, 32, and 50. And then I click OK. Then you pick the DFN, the control volume. You go to material, DFN, add DFN. And again, the program asks you which layers do you want to assign DFN, because the control volume is still crossing multiple layers. So I'm going to pick the jointed rock and click OK. And OK. And now you can see the DFN is assigned only in that region. Okay. So now I have the DFN. How can I run the model with the DFN? The next step is to do the divide all. So I use the default parameters. The divide all process is finished. I'm going to assign one automatic restraint to fix all the surrounding areas, the sites. And then I go and create the mesh. So I have around 100,000 elements, and now I can go and run the model. Here is the compute window. Excellent. So in less than 15 seconds, we could run the whole analysis. If you go to the results tab and activate the results on the exterior boundary, you can already see the effect of joints in the sigma 1 contour. So let me update it to the displacement and assign a cutting plane in a YZ direction. If I hide the exterior boundary, now you can see the effect of joints more clear. Okay, so this was our first demonstration, and I'm guessing you guys might have a lot of questions. So I'm passing it to Ali Reza to read some of your questions for me.
Thank you very much, Sina. Can you hear me?
Yes.
Okay. So there are a bunch of questions. I will just give you maybe 2 or 3. Bunch of them are related to assigning DFN. Is there any limitation for the number of DFNs that you can assign?
No, there is no limitation. You can define as many as DFNs as you have to the geometry. You can assign, for example, multiple DFN sets to the same volume. There is no limitation for it. Yeah.
That was the second question. So you can assign multiple DFN to the same volume or geometry.
Yeah.
Yes. There are a couple of questions about the statistical distribution of the joint. Like, for example, do you have the functionality to import from dips? If you have a joint set distribution in dips, can you import it, or any statistical distribution for the joint orientation?
So there is such functionality in RS2. For example, you can have feature that the orientation of the joints are also randomized, but in this version of RS3, no. We only have the uniform distribution for the orientation of the joints, but it is in our plan to give this functionality to the DFN tool. Regarding to importing to the dips, it is also it will be available in the next update of the DFN. But the workaround for it is to import the dips information to the Rockscience, the other new program that we release, and then from Rockscience you can bring it to RS3.
Just one more, then you can continue. Within the flow of creating this model, like when is it recommended to add the DFN to the system?
That's a very good question. As long as you have external volume in your geometry, you can assign the DFN. But the best time to do it is to assign it when everything is already, you define all the other volumes, you did all the divide alls for them, you assign all the cutting planes. When all of them are done, you did all the repair, add the DFN in the last step. Because if you assign it earlier, then the divide all process for the, let's say if you bring more geometry into your model, it can increase the time. So the best time is to add the DFN at the last step.
And after that, you do divide all?
You do the final divide all for the joints that you just added. Yeah.
Okay. Thank you very much. I have a bunch of more questions, but within the second round, maybe.
Perfect. Thank you so much, Ali Reza.
My pleasure.
Okay. So let's continue with the second demo. This demo is shorter, but it has one important, there is one important thing I want to emphasize here. So I have this simple external boundary, and I want to import the DFN and assign it to this volume. So I go to material, define DFN. This time I want to import DFN. So as you can see now, we have this complicated Voronoi joint network that was created somewhere else. Now I want to import it into the model. So I import it into the DFN tool. I click OK. To assign it to the model, once again, I select the volume. I go to material, add DFN, and you click OK. And the DFN is now brought into the model. The next step, you need to do the divide all to do the rest of the analysis. Some of you who are familiar with RS3, you might have the question that, okay, in RS3, you can bring any other surfaces, then assign it as a joint and do the divide all. What is the benefit of bringing the joint network, import it from the DFN, and then assign it to the model? The difference is in the divide all process. So as you can see, here I did the divide, and at the end, the original external boundary, the volume that I assigned the DFN to it, remained the same. It didn't divide it into smaller pieces. If I was doing it independent of the DFN and doing the normal divide all, it was giving me too many smaller volumes that are coming from the intersections of these small Voronoi surfaces. And then it would be populate your visibility tree. It would affect the performance. It would be a lot harder, for example, to pick the one side or surface of the external boundary. So my point here is when you are doing the divide all for a joint that is coming from the DFN, it is not splitting that original volume that you assigned the DFN to. It is smart enough to glue them back together, those small pieces, and keep the original shape of the external. These examples that I just showed you was basically a part of a research that was done in Dalhousie University, and we were collaborating with them. What they did, they assigned the Voronoi shape that I just showed you, and they did the UCS test and compared the results of RS2 and RS3 at the point of the failure. And here you can see the yielded joints when the specimen was failing, and the results are pretty close and, to be honest, very interesting. Now I'm going to continue by showing to you two of the applications of the DFN. The first example is slope stability. So I have this open pit, and we analyzed the open pit in two different scenarios. In the first scenario, I didn't assign any DFN to it, and I ran the SSR analysis. As you can see, the critical SRF was 2.86. And if I hide the exterior boundary, you can see the mode of the failure. Basically, it's failing in shear at the rock. And in the second scenario, this time we added the joints. So the shape of the joints basically are here. I didn't, for the first example, I didn't make them active. I think I have the model actually here. Yeah. Okay. So here are the joints. I hide the contour. An exterior contour. You can see I have two crossing parallel DFNs. And I repeated the analysis, and now you can see the critical SRF is dropped to 1.9, from almost 2.9 to 1.9. And you can see the mode of the failure has completely changed. If I hide the DFNs for you, you can see now, because I defined these weaker planes, now the mode of failure is sliding on these joint surfaces that I defined in the DFN2. So the point here was to show the importance of defining the DFN and assigning the correct material to see the actual failure of the geometry that you are dealing with. The second application I was going to show you was tunnel excavation in a jointed rock mass. So here you can see I have multiple layers. I have two cross joints defined here in these two layers, and also one parallel joint, one set of parallel joints that are crossing the tunnel. If I hide the joints and show you the steps of the excavation. So first we are doing the first part of the excavation, then I assign the liners around the tunnel, then I add the bolts and do an additional excavation. So this is the process of basically this tunneling for this example. And here we wanted to see the effect of the joints in the tunneling. So if I go to the results, you can see I'm just showing you the results at the last stage. You can see I'm just showing you the total displacement. You can see we have the maximum displacement where those parallel joints are crossing the tunnel faces. And if I also show you the results on the joint, and here I'm showing the relative shear displacement, you can see we have the maximum shear on this specific joint. In addition, you can also see the failure, which elements of the joints are failed. So I pick the shear and tension failure. And you can see most of them are failing in shear, most of the joints in the parallel, the parallel DFN. Because of the time limitation, I couldn't go through all the details of the DFN, but if you want to know more about it, I really recommend you to go and check out our help page for the DFN. We try to include all the details that you might need for your analysis. Beside the DFN, we also released two other cool features that I wanted to introduce them to you. The first one is advanced bolt selection. So let me go back to the last example that I was just showing you. I switched the results to the bolts. Okay, so for this model, we have 105 individual bolts, and these bolts are basically defined in multiple bolt patterns. So if I zoom in, I have 4 bolt patterns here for each step of the excavation for the tunnel. In the previous versions of RS3, we were showing individual bolt results in the visibility tree. So it was a lot harder for the users to pick the specific bolts that they want to see the results of it or graph the data. But now we made a major change. We are collecting all of the bolt results under the bolt pattern. So if you go to the first one or select any of them, you see a list of individual bolts under the bolt pattern. So if you select on them, you can see they are highlighted here. Also, you can see the location of the bolts, the location of the bolt head, where the bolt is touching the surface of the tunnel. And then you can, for example, graph the data and examine the results for that bolt. In addition to that, we have the advanced selection. So let me click on this. Here you see the whole list of all the bolts in your model. And all of them are basically collapsed under the name of the bolt pattern. And they are categorized based on different information, such as the location of the bolt head, the bolt property, the installed and the remove stage. So you can sort your the bolt results based on this information. For example, if in the last group I select on this header, you can see the data for the bolts are now sorted based on the location of based on the Z location. So it slowly, gradually increasing, and the last bolt has the basically highest Z location. This tab is also dockable, so you can move it. If you have, for example, two monitors, you can move it in one side and do your filtering. In addition to these options, you can define your own filtering. Here, for example, I want to see the bolts that, for example, the X value is between 10 and 14. So I click on the plus sign. I say, for example, the X value is greater than 10 and the X value is less than, for example, 14. If you click apply, now you see the list has been shrunk. So it's much easier for you to pick the bolt that you want to examine. Besides the advanced bolt selection, we added another feature which is called save and restart. So for big models and when you have multiple staging, sometimes for any reason your analysis might be stopped or canceled. For example, you have a model with 10 stages, you ran it until stage 5, and then let's say the power shut off, or you are at work, you want to turn off your laptop and go continue your simulation later on at home. In the past, if your analysis was canceling at the middle of the simulation, you needed to repeat all the stages that you have already calculated in the past and then continue. But now with this option in RS3, you don't need to repeat what you already calculated. From the stage that it was canceled, you can continue your analysis later on. So it can save a lot of time for you. This option by default is available. So if you go to project setting under stress analysis, the last option, enable file recovery, this is on by default. So you don't need to worry about the analysis if it was stopped or canceled for any reason at the middle of your analysis. Also, if you go to the compute, now you have two options in case you want to continue from the beginning or you want to continue from the last computed stage. So this is another feature that we added to RS3. At the end, I wanted to ask you, if you are already using RS3 and you have played with the DFN tool, I really appreciate if you can send us your feedback and if you have any recommendation for us. If you haven't used RS3 yet and you are interested to play with the DFN tool, please send us email. We can provide you a 30-day free trial. Okay. I wanted to thank you guys one more time. And also I wanted to mention that on November 9th, we are going to have another webinar, which is focusing on on-drain analysis and on-drain material that my friend Dr. Alireza Azami will present that. So if you are interested to know more about that, don't forget to register in the upcoming webinar. Thank you again, and I wish you a wonderful day. Goodbye.